So I can explain the mystery of the title as after Professor Étale refused to choose the title himself. I just, for symmetry, Professor Griffiths had already chosen his own title, which was Hodge theory from Abel to Deligne. So for symmetry's sake, I decided to make my title the Weil Conjectures from Abel to Deligne. Now I'm very sorry to say I don't know of any relationship between the Weil Conjectures and Abel. Or I'm sure there's one. So this talk is actually just about the Weil Conjectures. So my own introduction to the Weil Conjectures was a working seminar organized by UZ called Nearby Cycles, Perverse Shifts, and the Weil Conjectures, where I was to redo the construction of Lefschetz pencils by Nick Katz in SGA7 because Nick Katz used coordinates and Illusi thought that was unacceptable. So I got handed some handwritten notes of Deligne and spent several sleepless nights poring over them and shaking in fear. The thought I was making Illusi the next day, and I think at the end of the semester I still didn't know what the Weil Conjectures were saying or what a perverse shift was. My hope to this to make your introduction to the Weil conjecture easier than mine. At least I will try to at least state the Weil conjectures in a somewhat correct way. So as one not to start this talk with let X be a smooth projective variety over Q. So let X be a smooth projective hypersurface over Q. No, so okay, so the Weil conjectures are about algebraic varieties. So what's an algebraic variety? Well, like everybody says, it's something defined by polynomial equations. So let's take a polynomial. And to make my life simpler, in most of this talk, there will be only one polynomial equation. So the variety defined by one equation like this is called a hypersurface. But everything I will say is actually valid for more general varieties, except when I will say it's not valid for more general varieties. Okay, so here's a polynomial in n plus 2 variables with coefficients in some field. So you can take Q, R, C, a finite field, your favorite field. And we think, and this polynomial, I'm going to take it homogeneous. And we think of this as defining a hypersurface in projective n plus 1 space over this field K. So the reason I choose n plus 1 is I want my variety to have dimension n. That's all. And okay, so what's great about algebraic geometry is when I have something like that, well, it's not just the set of solutions with coordinates in K. Actually, every time I have a bigger field, L, containing K, I can look at what we call the L points of X, which is solutions with coordinates in L. So that would be the set of n plus 2 apples here, such that F is 0. And I'm in projective space, so this is up to scaling. The scaling is, I will identify x0, xn plus 1 with tx0, txn plus 1 for every non-zero t. Okay, and that's a set. Okay, and so for example, if I take n equals 1, I'll get a curve. I could take n equals 1, and I could take this equation. A, B are some numbers, like for example integers, and then you recognize the homogeneous form of the equation of an elliptic curve. At least if I didn't choose A and B too stupidly. Okay. So what can I do with this thing? Well, first let's look at if my base field happens to be C, then this, when I look at the C points, this is almost a complex manifold, but it can have singularities in that generality. So it's what's called a complex analytic space. So it's a very nice topological object, and I can ask some questions. For example, when is X a manifold? X of C a manifold? And I can even answer those questions, because in this case it's just defined by one equation. So I just look at the matrix of partial derivatives, and I want this to have no zero on X of C. Okay, so I'm just saying the tangent space has to be dimension n. I can ask, I don't know, is X of C connected? And if I know that this X of C is a manifold, it's also easy to answer. It's just asking whether this polynomial here is a product of two polynomials of smaller degrees. I can ask irreducible, yes. I can ask what does the fundamental group look like, the Betti numbers, the Hodge numbers. Okay. So that is not the kind of questions I want to talk about today. Well, I'll come back to some of these later, actually. The Weil conjectures are about what happens if my base field happens to be a finite field. So Fp is just means Z over Pz. The field with P elements. So for simplicity's sake, I'm just going to take Fp, but this I could take any finite field as a base field. And then if I look at X of Fp, well, looks it's just a finite set. So the only question it seems I can ask is, how big is this finite set? But as I told you, a variety, and you don't have to stop at the Fp points, of course. You can look at any bigger field containing Fp. So you can look at what we call Fp to the R, the finite field with P to the R elements, which is Fp with where I'm forcing some polynomials to have roots. So here I'm going to add all the roots of all the P to the R minus 1's roots of unity. And that's Fp to the R. And then the Fp to the R points of X are also a finite set, so I can look at their cardinality. And now that becomes more interesting because I have a sequence of numbers. So the question is, how do they grow, for example? And well, so this X if I come back to the topological point of view for a minute, because that actually informs what we do over finite fields. This X as a complex manifold, it has dimension n, which we can actually make sense of even in this case, and unless I chose a stupid equation like f equals 0. And so an n-dimensional space, yeah, I should say something, although that there is a there's also a definition of X smooth in this case. And actually the definition is just you take the Jacobian criterion over C, but then now your equation, all your equations have coordinates in this finite field, but then you can just say, okay, I'm going to say that I'm going to define a smooth hypersurface to be one such that this criterion is satisfied, and that's actually a good notion. And Same for x connected. So all these things that can be characterized algebraically have equivalence. Well, the reason I'm doing that is that if x is smooth and connected, then what would you expect for its number of points over fp to the r? Well, okay, think about the simplest variety you can imagine. For example, a fine n space. It has over a field with p to the r elements, it has p to the rn elements. So that should be the leading term, and then there should be error terms. And so the question is, what are these error terms like? Okay, so that's an interesting question. You're counting solutions of this equation over finite fields, which actually I think was very close to the title of Weil's 1949 article, where he stated the conjectures, something like on solutions of equations in finite fields. Also, I just want to mention what I think is the most fun case when your base field is Q, so your polynomial has coefficients in Q, then chasing denominators, actually, you can make it this thing to have coefficients in Z, sorry, n plus 1. Chasing denominators is harmless because I'm only looking at solutions up to multiplying by a constant anyway. Oh, well, I mean, what I'm saying, it's even simpler than that. Chasing denominators won't change the set of solutions. And then this x, I could talk of its C points, and I could talk of its FP points for all P. And then I can look at all the problems at the same time and ask, is there really any relationship between these problems? And of course, if I'm asking, the answer will turn out to be yes. Okay, but now let's come back to finite fields. So here's the theorem. And that is the first case of the Weil conjectures. It's the case where x is a curve. So if assume that n equals 1, so x is just defined by one equation in projective through space. And also, I'm assuming that all these properties are satisfied, so this equation is reducible, and this condition is satisfied, except not on x of c, obviously. And then so the leading term of the number of fp to the r points of x is p to the r in this case, and then the error term is big O of p to the r over 2. What? Well, you don't need x smooth. Yes, okay. You do need irreducible. Yes, but well, for what I'm going to say actually, it's more precise. Yes. 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 Which I'm going to say right now. Yes. So actually, what he proved this number of points. So there's p to the r plus 1, and then there's a sum alpha 1 to the r, etc., plus alpha g to the r, where yes, thank you. Where g is the the genus of the curve. So if we were, so the genus, if we were over C, the curve is a Riemann surface. So it's a donut with a certain number of holes. The number of holes is the genus. Now, I'm not going to define it over a finite field, but if we are in this case, and if I choose a P that is large enough, so I don't have problems when I reduce the equations modulo P, then actually the genus of the curve, when I look at it over Fp, is the same as the genus over C. So I have this thing that lives over Q. Over C, it's a donut with G holes. And now when I start counting Fp points, this G comes back here. Okay. So G is the genus, and these alpha i's are algebraic numbers, even algebraic integers, and satisfying absolute value of alpha I is square root of P. Now, okay, before somebody stops me, I know, so this does not make sense, as I stated it, because if I have an algebraic integer, say 1 plus square root 2, then I have many ways of seeing it as a well, in that case, 2 ways of seeing it as a complex number. I could just as well, so 1 plus square root 2 is just defined as the solution of some equation, and I can't distinguish between the solutions of the zeros of an irreducible polynomial, and so I could just as well think of this as, when I see it as a complex number, it could become 1 minus square root 2. Or, so when I write this, actually what I mean is for every embedding the algebraic numbers into C, the image of alpha I has absolute value square root of P, which is a much stronger condition. For example, this one, its 2 images don't have the same absolute value. And by the way, I will use this notion again and again. So such an alpha I is called a Weil P number of weight 1, and a Weil P number of weight W would be is the same, but now the absolute value becomes P to the W over 2. Okay. So anyway, so that's what he proved. This, and then of course from this follows, because this alpha I to the R are bigger of P to the R over 2. And yes, the algebraic integers, yes. And so the question would be, well, how is there a way to generalize this to higher dimensional varieties? How? So, okay, so you have a sequence of numbers. You want to study it. So if you've ever done any combinatorics, the way to do that is to introduce the generating series of that sequence. And one very good way to do that. So let's introduce this generating series, and it's called the zeta function of x. It actually turns out the right series to look at. I will explain later why. Well, we'll try to explain. Is not sum of TR cardinality of Fp to the R points of x. It's this one. So I take this sum. I take the exponential. So this a priori is just a power series in T with rational coefficients. Okay, so let's look at some examples. Do I have time for examples? Probably not, but let's still look at some examples. So if x is Pn, so you could take the equation, for example, projective n plus 1 space. So let's just take the hyperplane xn plus 1 equals 0. And then this thing, well, I have p to the Rn points coming from the affine space in there, and then I have the hyperplane at infinity contributing p to the r times n minus 1 point, and then at the infinity of that, I have the affine space of dimension n minus 2, and then it goes on until I get to the point at infinity of infinity of infinity, etc. And then when I calculate the zeta function of this, it becomes very nice, because the sum here is going to be turned into a product by the exponential. And here, of course, you all recognize the power series. So this is minus log of 1 minus p to the rt. So when I exponentiate, I get this. So this is not just a power series. Oh, yes, thank you. P to the j, yes. This is not just a power series, it's actually a rational function. And in the case where x was a curve, using Weil's theorem, you can calculate the zeta function, and you get 1 minus alpha 1t, 1 minus alpha 2gt divided by 1 minus t, 1 minus pt. Okay, so does anybody see a pattern here? No, you can't answer. So yeah, I wanted to try to keep them. So after doing this, and one assumes a few more examples, Weil made the following conjectures. So here, x is supposed to be smooth and connected. First, that this, yes, sorry, I will raise it eventually. First, that this zeta function is actually a rational function of t. And then, second and more precisely, that its numerator and denominators have some very precise forms. So here, n is the dimension of x. So x doesn't have to be a hypersurface for this. It could be any smooth connected projective variety. So the numerator and denominator are written like this, where these pi's first, these pi's are polynomials with integer coefficients. So their roots will be not just algebraic numbers, but algebraic integers, like in the case of curves. Let's normalize them to have constant term 1, and then that the roots, or rather the reciprocal roots of these pi's, let's call them alpha ij, should be Weil numbers. of weight I. They are p numbers, so that means they are algebraic integers, and that means their absolute value, no matter how I send the number into C, their absolute value is p to the I over 2. So in particular, that will tell me, that will give me some estimates about the number of points of X over finite fields, but that is much more precise. So this is the part that is called the Riemann hypothesis over finite fields. This is, so if my zeta function is to be a zeta function, it should have a functional equation. Functional equation in this case will look like this. So if I replace t by 1 over p to the n t, I get up to a sign, a power of t and a power of p. I get my zeta function back. And what is the power here? Chi is sum of minus 1 to the I degree of pi. And why did I call it chi? Why? It's a Lair-Poincaré characteristic, of course. The last one is if x comes by reduction modulo p from some big X over Q, as before, then this degree of pi is the Betti number, the Betti number of the C points of this thing. So like in the case of curves, the genus is 1/2 the first Betti number, and it will tell you the degree of the numerator of the zeta function. Well, that also generalizes. Okay. So those are the Weil conjectures. If you So I'm actually glad I was given the Weil conjectures and not Hodge theory, because this is a pretty concrete conjecture about just, you have an equation, you count the solutions, how many solutions you have, and all that. Okay, so of course, so I guess I should try to answer the question, why are the Weil conjectures called the Riemann hypothesis for varieties over finite fields? So what's the relation to the Riemann hypothesis? Oh, it's very simple. You look at Z, the ring Z, and instead of just thinking of this as the ring Z, I'm going to say that Z will be the ring of polynomial functions over a curve, an algebraic curve, which I'm going to call spec Z. Of course, that's in algebraic geometry is tautological, because spec Z is just the name for the algebraic curve whose ring of polynomial functions is Z. So now, what does this curve look like? Well, okay, how can I get at the points of such a thing? Well, the first thing is, I've told you this is a ring of functions. So there are functions, they are defined on spec Z. Where do they land? So in algebraic geometry, functions can have, they don't land in some fixed space. They can land in any field, have values in any field. So we think of a point as something on which you can evaluate a function. So a point would be like a map from Z to a field, for example, Fp, which we think of as evaluation at X. So the map sends F to the F of X. And here, okay, and this is a map of rings. See, evaluation maps are maps compatible with addition and multiplication. And here, of course, you stop me because you say, well, these are not all the maps that I have. I could also send Z into Q. That's also a nice map of rings. So, okay, but then I get a different kind of point. It's dense in spec Z. Okay, so yes, algebraic varieties have closed points and then they have bigger points. And closed points, in the case of spec Z, correspond to these maps. So I have 1 point for every prime number. So if I try to draw spec Z, well, there are many ways to draw spec Z. I'm drawing it as a surface because an algebraic curve topologically has dimension 2. And I have points for all the prime numbers here in no particular order. And then I have a big dense point that is corresponds to the embedding into Q, and that we call spec Q. Yes. So you got the joke. Yes, 57 is the Grothendieck prime number. That's the example that Grothendieck took when he wanted a prime number. And now the Riemann zeta function is, as you probably all know, is defined to be this this nice Dirichlet series, and you can also factor it as the product over all prime numbers of 1 over 1 minus p to the minus s. So that wasn't me. This is a product over. So this is a product over all the closed points of Z. Now, what happens if I am over a finite field? Let's take. So this spec Z is a curve. Let's take X a curve over FP. Okay. So the thing is, the curves I've looked at before, they are compact in some way. So this spec Z is not compact. It's missing a point at infinity. So if I want to make the analogy complete, I'll have to remove a point at, or several points at infinity in this curve. So this X is going to be given by an equation G of x1, x2 equals 0 in a fine 2 space. So that means in my equation that I had before, for example, I set x0 equals 1. I remove the line at infinity. And now, well, the reason I'm doing that is that now all the information about this is contained in its ring of functions. So the ring of functions on X, let's call it A, is going to be, so it's the ring of polynomial functions on X. So it's polynomial functions on the plane, and then modulo the relation that G equals 0. And so if I want to do the same, a closed point X of this will correspond to a map from A to some finite field, which here could be bigger than FP. And of course, even here I was taking the map modulo some equivalence relations. Like the map Z goes to FP or Z goes to FP and then embeds in FP squared. I'm taking them to be the same point. So same here. Okay, so a map like this, and I'm going to set n of x is e to the r if r is the minimal, I mean, if r is the smallest r such that the map lands in fp to the r. And they want to, oh, yes. And, well, what is a map like this? It means I'm choosing the images of x1 and x2 subject to this relation. So it's the same as some point in x fp to the r. Again, there's some equivalence relation there. Okay. So now if I'm looking at the product over all x, the closed point of this curve, of this thing, which is the exact analog of my zeta function over there, then it's a easy lemma to show that this is equal to the zeta function of x evaluated at p to the minus s. And this has nothing to do with algebraic geometry. Right. Well, I mean this lemma here. And so, okay. So this is why this zeta function of this curve over a finite field is the exact analog of the Riemann zeta function. So in this case, we would think the Riemann zeta function is the zeta function of spec C. And there's actually a notion of zeta functions for any, well, I guess, for example, any variety over Q, if you want. But there's a fundamental difference between these two. The Riemann zeta function is not a rational function of anything. That is very important. This is why one reason why the situation over finite fields is so much simpler, because it's much easier to get at the pulse of a nice rational function, for example. Okay. So now I'm never going to talk about the Riemann hypothesis again. Oh, okay. So this is called Riemann hypothesis because it tells you where, of course, the zeros of this zeta function are. Now I want to try to give some heuristic justification for the Weil conjectures. And this is going to be very wild. So, okay, first I need FP bar. So, yes, I'm tired of finite fields. So let me look at this, the algebraic closure, an algebraic closure of FP. So instead of looking at points with values in some FP to the R, I could just look at points with values in their union. And the reason I'm doing that will become apparent in a moment. On this thing, I have an endomorphism, let's call it phi, which is called the Frobenius endomorphism. It's the second reason finite fields are so much easier to deal with. So this is raising to the p's power. And this is a morphism of rings. So that means it's compatible with addition and is compatible with multiplication. So the fact that it's compatible with multiplication should be clear to everybody. It sends products to products. Why does it send sum to sums? If you've never seen it, it's a simple calculation. Phi of x plus y is x plus y to the p. So you use the binomial formula. You have x to the p, y to the p, and then the other terms are just a sum of x to the y, y to the p minus 1 times binomial coefficients. But this binomial coefficient, if I is between 1 and p minus 1, that's a multiple of p. And so if you are in one of these fields where p is 0, well, that just disappears. And why is this Frobenius interesting? Well, if you remember, fp to the r, I told you, is just fp where I add all the p to the r minus 1 roots of 1. But of course, x to the p to the r minus 1 equals 1. I could just, it's just almost the same as x to the p to the r equals x. And what I'm saying here is that fp to the r is just the fixed points of phi to the r in FP bar. It's just all the elements there that are equal to their own p to the r's power. Right. Now this thing here, so in particular this thing is a ring morphism, and on FP it doesn't do anything. Okay, if I take an element of FP, raise it to the p's power, I get back the same element. And so if I have my variety again, it's defined by a nice equation. And this equation has coefficients in FP. And so that means if I have a solution of this equation and I apply Frobenius, I get another solution of this equation. So if I look at the FP bar points, then this thing acts, preserves the solutions. And then, of course, how do I recover the points on Fp to the r? I just take the fixed points of the r's power of Frobenius. And the last thing is, well, this is not just some random thing that permutes the solutions here. This phi actually comes from a map on the level of varieties. Let's call it F. I'm not going to risk making a sign mistake by telling you the name of F. Let's just say there's a map. And when I look at the map on points, I get back this phi. Okay. So why is that great? Well, let's suppose for a moment that this variety and this F are defined. They're not over finite fields where we don't know what to do, but let's assume they're just over C. They are complex varieties. So I have a complex manifold, and I have an endomorphism, and I'm telling you, you know, I would like to count the fixed points of this endomorphism. So of course you're telling me Lefschetz fixed point formula. Okay. Well, we have to check that the fixed points are isolated and things like that. But look, the differential of this map is just p times something, right? So it's 0, right? So this f is contracting, right? This differential is less than 1. So it satisfies all the hypotheses I would like, and the Lefschetz fixed point formula is just going to tell me, well, this number here is equal to the trace of, it's the trace on cohomology, so let's just write it like this. It's the sum of -1 to the I times the trace of this operator induced by f to the r on hi of x, with coefficients in Q, for example. And so that's great, because here linear algebra to the rescue tells me when I take an exponential involving the trace, I usually get out a determinant. So if I actually calculate the zeta function, it's a very easy exercise to see. You get the product over I odd of determinant of F1 minus this F star T on HI over the product over I even of the same thing. Hey, does that look familiar? Okay, so that means let's set this to be pi of t. Then that's part 1 of the Weil conjectures. It's part 1, and that's also part 2a. Check. Okay, now part 4 is kind of irrelevant in this fantasy world. Part 3 is just going to be Poincaré duality. At least once I know 2b, part 3 just reduces to Poincaré duality. It says that hi and h2n minus 1 are dual. And, well, what about 2b? Well, for 2b, there's a theorem of I think it's there. It tells me if X is a complex projective manifold, and if, say, F is an endomorphism of a map from X to X, such that F, so I embedded my manifold in Pn, so I can look at this line bundle on Pn, restrict it to X, and take its first Chern class, and look at what F does to it. And let's assume it multiplies it by some number Q. And if you don't like Chern classes or line bundles, or you don't know what Chern classes are, if X is a curve, this is actually equivalent to saying that F has degree Q. But in general, this is stronger. And then, if this is true, then the eigenvalues of F star on Hi of X have absolute value square root of Q. No, sorry. Square root of Q to the I. And that's an exercise in Hodge theory, so I'll ask you about it at T after you've seen the Hodge theory talk. It's 2 to 7, right? Yes. Okay, so that now it's not very hard to check that my Frobenius satisfies this property. I agree, I think. Well, so now I have part 2b. Great. The Weil conjectures are proved. So now let's come back to the real world. So this is inspiration. I think I'm not sure if Weil believed that that it was possible to actually realize this over finite fields, but apparently Grothendieck did. So Grothendieck's approach is, well, okay. Now we are not obviously, we don't have Betti cohomology, so let's make a cohomology that has the same properties. So define the cohomology theory. For X over Fp, or another finite field that has properties similar to Betti cohomology. Over C. And this is what's called Étale cohomology, or even Étale LID cohomology. So he wanted to do. He succeeded with the help of other people, most notably Artin. And he succeeded a little too well because he didn't define one cohomology theory, he defined a whole family of them. If I want to be, don't want the experts in the audience to yell at me, I have to write the cohomology groups like this. So these things, you can't make them have coefficients in Q. That's the only small problem. You have to make them have coefficients in QL, the field of L-adic numbers, where L can be any prime different from P. And it's, of course, that raises the question, you know, what happens if I vary L? But anyway, let's just choose L equals 2 because I never want P to be equal to 2, and then I can do that. In practice, it doesn't really matter most of the time. And this has a Lefschetz fixed point formula. It has Poincare duality, and so once you actually establish all the properties of this, then this thing will just follow from general theory. So I should mention there was another proof, earlier proof of one by Dwork that used p-adic methods. As Grothendieck's way apparently was just to make a very general theory, and then everything you want follows trivially from it. Well, almost everything. As for 4, it follows from the fact that if you have something over a variety over Q, then there was a comparison result between the Betti cohomology of its C points and the Étale cohomology of its FP reduction. But I want to talk about 2B. Okay, 2B was the problem. There is no, so this thing is very nice property, but there is no Hodge theory over finite fields. And so how would you prove 2B? Well, Grothendieck also had an idea. He had this idea that underlying all this variety of objects, there was something mysterious hiding there called a motive. And these motives should have some properties that whose list was inspired by what happens over C. So he had a whole list of conjectures called the standard conjectures. And if you can just prove the standard conjectures, then the Weil conjectures will follow formally. Okay. Unfortunately, nobody can prove the standard conjectures. So that's a bit annoying. So they will follow formally in a way that's very analogous to the proof of Serre's theorem over C. That's very satisfying. The only unsatisfying thing about it is we can't make it work. It's a small problem. So what did Deligne actually do? So okay, what to do? Because the Weil conjectures are proved, as I hope you know. Yeah, I forgot to mention that. They're not conjectures, he proved them. but the standard conjectures, they are conjectures, most of them. So what to do? Yes. Well, let's consider, instead of just looking at a variety all by itself, consider families of varieties. So you have a basis, and then you have a family. So the basis is itself an algebraic variety, and this is a map of algebraic varieties, and the family means for every point in the basis you have a fiber, which is an algebraic variety, and then the fibers, you know, they vary in some way. And when you have something like that, well, if you look at the hi of a fiber, this gives me a family of vector spaces over the basis, also known as, at least in topology, this is known as a local system. So here I am assuming the fibers are nice to get a local system. So they don't have singularities, for example. And what is a local system? A local system also is the same as a representation of the fundamental group of S and some finite dimensional vector space. And here's an example of family. And the nice thing is, yes, these are this kind of way of building family kind of blew my mind the first time I saw it, because well, let's look at the hypersurface defined by this equation f, but instead of just looking at the hypersurface, I'm going to say, okay, this is a family over the space of all equations. So of all, say, degree D homogeneous polynomials. F and up to scaling. So that means the basis in this case is just some projective space. So this ND would be the dimension of the vector space of degree D homogeneous polynomials in n plus 2 variables. Okay. And then if I want to have a nice family, I remove the bad polynomials, but the bad polynomials, if you remember, were defined by algebraic conditions. And so that's a very nice family. Very relevant too. And okay, so in the 0 minutes that I have left, I'm going to tell you quickly how you would go about proving the Weil conjectures. So this is slightly different from the original proof, but still, mostly it is the original proof. So if you have a family like that, okay, so first you prove something like, okay, if I know the Weil conjectures for every fiber xs, except for maybe a finite set of points, then I can actually propagate them to the whole family. It's actually, yeah, that's you have to think about it, but then it's not that hard to prove. And there's even a version for bad fibers. So even if maybe those missing fibers had singularities, I can still say something about them. Like they have, let's say I have semi-stable reduction, so they have some irreducible components, but the irreducible components are smooth. Then I can still say something about the cohomology of these irreducible components. Second thing, if the local system here is irreducible, so that means this is a representation of the fundamental group. Let's assume it's irreducible. Then I know the Weil conjectures, and this is, I think, this is the deepest part. Well, so here I should say, what you really do is, usually you just reduce to proving all your estimates for Hn, if you're in dimension n, because induction will take care of the rest. Induction and the Lefschetz hyperplane theorem. So I'm just looking at the local system for I equals n. Okay. So if this is irreducible, then actually this was, there's a better version of that. I don't even need it to be reducible, but then it could get more complicated. If this is irreducible, then I know the weights of the Weil numbers that will appear are going to be the same. They're going to be there's going to be one weight appearing, and it's going to be the same for every point. Okay, and then if n is odd, then the L in my example is irreducible. My example of hypersurfaces. Oh. Sorry, I should mention in 2, actually, I know all my eigenvalues of Frobenius on the cohomology of the fibers have some weight, but I don't know the weight is n. It could be n plus something. So I know the Weil conjectures up to some translation. But yes. Well, then 4 would be reduced to the case of hypersurfaces. So something like every variety is called actually every variety is birational to a hypersurface. And then, 5 test a particular variety. To get rid of the uncertainty on the translation. I don't know, Pn, for example. Yes. And then, okay, just something to do for n even, but it's good. Okay, at this point it's not too hard. And okay, you've proved the Weil conjectures. So modulo this. So these 2 here is where, well, fortunately I'm out of time, but this is where the Rankine method appears. So you're saying, okay, there is an a priori trivial estimate on the weights appearing in this L. Now let's look at big tensor power of L, L to the n, and there is an estimate, and then there is another trivial estimate, and then let's just find a way to relate the weights of L and L to the n, and this way the estimate for L to the n gives me a better estimate for L, and then I make n go to infinity, and I get my theorem here. That's roughly the way it goes, very roughly. Thank you.